Bismillahirrahmanirrahim. Assalamu alaikum dear students. This is our next problem. Problem having been chosen from the book Modern Physics by Kenneth S. Crane. As usual, we first come to its statement. Okay. The electrical conductivity of copper at room temperature is 5.96 into 10 to power 7 ohm inverse meter inverse. Okay, this is the symbol of ohm. Okay, ohm in electronics is the unit of resistance or perhaps also resistivity. This is okay. So when ohm -1, it means 1 over ohm. Similarly, meter inverse means 1 over meter. Okay. The electrical conductivity of copper at room temperature, it is hereby further clarified that, dear students, there is also some conflict or confusion about the appropriate room temperature. Okay, it varies slightly. Okay, however, to the extent of this problem, and mostly we take room temperature as equal to 20 degrees centigrade. Okay, so we convert 20 degrees centigrade into Fahrenheit and say also in Kelvin absolute temperature. Okay, so it is hereby clarified that room temperature usually for the purpose of our solution of problems of this nature, that is solid state physics, room temperature here has been taken or chosen as 20 degrees centigrade. Okay, evaluate the average distance between electron scatterings. Average distance. Okay, how many lattice spacings does this amount to? Okay, yes students, actually at the end we will compare our result with the spacing with the average distance between electron scatterings, and this value is also given in the tables, various tables used in used in solid state physics. Okay, anyhow, we first move to helping tool. Okay, first helping tool has been shown in two alternate versions. Okay, first version says that it is equation number 11.19, and the second version says that this is equation number 11.3. Actually, dear students, both these versions have been chosen, both these snapshots have been chosen, have been selected from the same book to which book this problem relates, that is Modern Physics by Kenneth S. Crane. Actually, that is rho is equal to ne square tau over m, equation number 11.19 has been taken from in between the chapter, while its alternate version, which is equation number 11.3, but actually this is not equation number 11.3. This indicates that this snapshot has been chosen from the summary given at the end of the 11th chapter of Modern Physics by Kenneth S. Crane, and this indicates that this conclusion or this result belongs to third topic of 11th chapter of Kenneth S. Crane Modern Physics. Okay, so in its alternate version, this thing has been more clearly described, that conductivity of free electron gas rho is equal to ne square tau over m. Okay, dear students, it is hereby clarified that electrical conductivity is denoted by this symbol rho, while thermal conductivity is denoted by capital K. which also stands for Kelvin. Okay. Moreover, this E is electronic charge, which is a constant value we will choose from table of physical constants. Similarly, this tau is a time between collisions. Okay, anyhow, in our explanation section, we will elaborate this expression in a relatively more comprehensive manner. Okay. In our explanation section, we will develop a foundation to define this expression properly, and hence in our explanation portion, this expression will be discussed in a relatively more comprehensive manner. Dear students, in helping tool number 2, a table has been shown. Okay, table. What is important in this table? We see that 1, 2, 3, 4. At number 4, copper comes. Copper or cuprum, because copper comes from Latin name cuprum. That is why its symbol is not CO. This is CO, perhaps this is for cobalt. Okay, that is why copper is denoted by Cu, because its Latin name is cuprum. Okay, so Cu stands for copper. Yes, students, this is nearest neighbor distance in nanometer, 0.256. This figure will be used in our solution. Rather, it will not be used, just it will be compared, because in the last portion of our statement we are asked to compare spacing. Okay, we are required to give the estimated number of spacings in comparison with this distance. Okay, so the result which we will arrive at the end of our solution will be compared with this value, that is 0.256 nanometer. 0.256 nanometer, which is the nearest neighbor distance. This distance will be compared with our calculated value, and from this comparison we will find how many spacings exist. Okay. Tool number 3, electrical conductivity of metals at 300 Kelvin. Okay, dear students, the copper measured rho, that is electrical conductivity. Electrical conductivity is denoted by rho in ohm meter whole inverse, that is ohm inverse meter inverse, 1 over ohm meter. Okay. Dear students, the purpose of this table, actually we do not need this table very much to the extent of this table, to the extent of this problem, but here actually the purpose of this table having been included in our helping tools is just to develop a confidence that even if this value of electrical conductivity of copper at room temperature, that is 59 into 10 raised to the power 6 per ohm per meter, is not provided in this statement, we can choose this value, we can take this value from this table. Okay, this value, dear students, okay, copper 59 into 10 raised to the power 6 per ohm per meter, this value is given in the statement, so we primarily do not need this table, but purpose of this table is to develop a confidence that even if this value is not provided in the statement, we can take this value from such tables of constants which are very widely used throughout books of solid state physics. Okay, solid state physics books are full of such tables. Okay, Moreover, dear students, one thing more needs to be clarified here, that this table says that electrical conductivity of metals at 300 Kelvin. Why 300 Kelvin? Actually, the situation is that I had previously, I have mentioned that room temperature is not a very exact figure. It slightly varies in various times, in various circumstances. Okay, so in this problem we are taking room temperature as 20 degrees centigrade. Okay, so we will convert that 20 degrees centigrade into Fahrenheit and Kelvin. So when we convert 20 degrees centigrade into Kelvin, it becomes about 293.15 Kelvin. Okay, so 300 Kelvin and 293.15 Kelvin are close to each other. Okay, so we can assume that this temperature, that is at 300 Kelvin, is for our facility that it is at room temperature. Okay, if we assume room temperature as 20 degrees centigrade, then its result in Kelvin becomes 293.15, and we know that 293.15 and 300 are very close to each other. So this temperature, that is 300 Kelvin, indicates room temperature. Next, from tool number 4, dear students, we will take this value, electron. Okay, minus E 9.109 into 10 to power minus 31 kilogram. This alternatively becomes equal to 5.486 into 10 raised to the power minus 4 atomic mass unit U. We will take this first value. Okay, now we come towards table number 5. Okay, table number 5 has been used so many times that we skip this tool for the time being. Tool number 6 is also a very important table. Okay, in this table 1 2 3 4 5 6, at serial number 6 or row number 6, 6th row, copper or cuprum has been described. Its Fermi energy is 7.0. Its Fermi temperature is 8.16, and its Fermi velocity is 1.56 into 10 raised to the power 6 meter per second. Okay, so dear students, this table is also very important. Okay, from this table we can take Fermi velocity of copper, that is 1.57 into 10 raised to the power 6 meter per second. Okay, we can also take its Fermi energy, which is 7.00 electron volt. Okay, we can also take its Fermi temperature, which is 8.16 into 10 raised to the power 4 Kelvin. Anyhow, now we come to its solution. Okay, we know that conductivity of free electron gas is given as rho, that is electrical conductivity, is equal to n E square tau over m, equation number 1. Rearranging equation number 1, we get tau equal to rho m over n E square, equation number 2. Here we explain what are these factors. Okay, where small n is the number of density of conduction electrons. Okay, where small n is the number density of conduction electrons. Where small n is the number density of conduction electron. Small e is the electron charge. Tau is the average time between electron ion collisions, and we are going to determine this value of tau. Okay, while remaining values are given, already given. Okay. And m is the electronic mass. Okay, m is, for m we have also described a helping tool. Tau is going to be determined, value of rho is also given, value of n is also given. Now we use these values in it. Okay, using electrical conductivity rho equal to 5.9 into 10 raised to the power 7 per ohm per meter. Okay, dear students, actually this value is given in the statement, but even if it is not given in the statement, we can choose this value from table which we have shown as a helping tool. Moreover, this m, that is mass of electron, is also given in the helping tool, 9.11 into 10 minus 31 kilogram. And this is also given in the table here. Okay, 8.47 into 10 raised to the power 28 atoms per meter cube. Yes, students, we see here, we will go back to tables whether we see that yes, perhaps it is missing. That table perhaps has been missed. Actually the value which we have used is given in some table, but unfortunately perhaps that table has been missed from including. Okay, yes. Anyhow, we have explained here that using this value equal to this value equal, okay, this value is provided in the statement and this is also given in the table. This value is a constant value which is also given in a helping tool. This is actually in some other problem we will include, this table will be included in which this value will be given. Okay, this is also a constant value and is given in a large number of tables given in the books of solid state physics. Okay, unfortunately by mistake that table has not been included in our helping tools, but it is confirmed that this value, that is n equal to 8.47 into 10 to power 28 atoms per meter cube, is a constant value. Okay, and is given in the relevant tables. Okay, and here electronic charge, elementary charge is also given in the table of physical constant. Okay, so we will put all these values in equation number 2, and hence nothing else, just simplification. Okay, just simplification. Here, dear students, actually the situation is that this meter cube is in minus, so it will be shifted to a numerator and it will become m plus 3. So this m minus 1 and this m plus 3 resultant value will become m plus 2. Moreover, dear students, actually there are lot of conversion factors used in this portion. Okay, all those conversion factors have not been shown, because if various tables regarding conversion factors are shown as helping tool, then a list of helping tools becomes large enough. Okay, so it is understood that we know conversion tables, conversion factors which are given in various tables. Okay, so here we see which conversion factors have been employed. Kilogram meter. Actually here, dear students, conversion factor of Coulomb has been chosen. then various units combine and form Newton, then Newton meter, and here watt becomes as alternate unit, here volt becomes, here ampere becomes, okay. So dear students, actually it is quite to the extent of numbering, this is a very simple calculation, but units involved are complicated and they are converted to other units frequently. From this point of view, this calculation is slightly complicated. Anyhow, when we solve this portion carefully using adequate tables of conversion factors, we reach this conclusion that tau finally becomes equal to 2.5 into 10 to power minus 14 second. Okay. After employing a number of conversion factors, we conclude that value of tau finally becomes equal to 2.5 into 10 to power minus 14 second. Now, next, dear students, this is another expression that L is equal to tau Vf. We have to find out this value L. Here we also explain what is L and what is Vf. Okay, for the time being we are directly using this result that L is equal to tau into Vf, where F is written as a subscript of V, that is Fermi velocity. Tau is the value which we have calculated in above portion. Okay, so L is we are going to determine. Okay, L is equal to tau into Vf is equal to this value which we have calculated in above portion, and this is the value which is given in the table. Okay, we have emphasized this value 1.57 into 10 to power 6 meter per second. This value is given in the table of constants. Okay, I have emphasized that solid state physics books are full of statistical data in form in the shape of tables. Okay, and we cannot proceed without understanding those tables. Okay, so after simplification, this second will be cancelled with second and our answer will become in meter, and these 10 to power this 10 to power minus 614 will be adjusted with 10 to power 6, and resultant we will get 10 to power minus 8. But we know that 10 to power minus 8 is not very much important for us. What is important for us is 10 to power minus 3 or 10 to power minus 6 or 10 to power minus 9. So we convert it in 10 to power minus 9 so that it will be termed as nano. Okay, so our L becomes equal to 39.2 nanometer, where L is the mean free path. Okay, this term is appearing first time in our problems. Mean free path, where L is the mean free path of the electrons, and Vf, where F is written as a subscript of V, is the Fermi velocity. In comparison with 0.256 nanometer, this value was also given in the table. We had emphasized that in the end we will compare this distance with the calculated value. Okay, so this value 39.2 nanometer is going to be compared with this value 0.256 nanometer, and on the basis of this comparison we are going to conclude that in comparison with 0.256 nanometer, this amounts to 153 lattice spacings. Okay, what we have done, actually we will divide this figure by this figure and we will get the result of 153. Okay, so 153 is the final lattice spacings. Okay, and this is the end of our problem and this is the end of our video. Till next video, Allah Hafiz.